Hello everybody, this is Sam from HiPy. Today we're going to be talking about hypothesis testing. We have a very short introduction to why we do hypothesis testing, and then we have a very simple example of a hypothesis test. So I'm going to really labour this point because it's very important that we kind of understand what's happening here, but we're going to talk about what is a hypothesis test. So a lot of the time in science and maths, in the real world, we have some kind of data which has some kind of random influence on the result. So, for example, IQ tests, kind of chemical experiments, physical experiments, that kind of thing. Kind of not really population, well, kind of population because there is kind of some variance in that. But there's a lot of data which has some kind of random element to it. So a lot of the time we want to be asking questions, and then we'll get some kind of result, and we'll pick some kind of observation or a sample out of that population, and we'll say, is this kind of sample or observation what we'd expect? Or is there some kind of difference to, or is there some kind of change that we need to make in our model? So, for example, here we've got the normal distribution. And say we have a situation where we have some data which is perfectly normally distributed, or we assume it to be perfectly normally distributed with mean 0 and standard deviation 1. So this is what we're looking at here. This is the distribution. So if we got a piece of data back which was just 0, we'd say, oh yeah, that's kind of like really good. That's what we'd expect because it's within kind of like the realms of possibility here. If we got a piece of data out which was 1.5, we'd see here that we're kind of quite far out here. We would be like, if we have a piece of data like that, we'd be like, oh, I'm not sure that that's okay, but statisticians say the probability of something happening based on a null hypothesis before we start to ask questions is around about 5%. So at 1, we see here that we're hitting about 25% of 1 happening, or sorry, 1.5 happening, or worse. And that's important. We want to be looking at kind of like the line here down to 1.5 or to the right of this. So the chances of 1.5 happening or worse is a very rough estimate of about 25%. I haven't worked that out exactly, but it's around about 25%. So that's within the realm of possibility. That's like saying if we flip a coin 2 times, what's the chance that we get 2 heads? We wouldn't say that the coin is unfair or biased because we got 2 heads in a row. That's a little bit ridiculous. But as we start getting over here to the 2s and the 3s, we'll see that the probability of getting that or worse is a lot less. And then we start to get to the point of kind of 5%, 2.5%, so we can start to say maybe our model's wrong. Maybe the mean isn't at 0. Maybe it's more up here. So that's the essence of hypothesis testing, is that we have a null hypothesis where we say, I think that, or our current model suggests that the mean is 0, and then we have an alternative hypothesis which says the mean is not 0, or the mean is greater than 0. And those hypothesis tests are what we're going to be using to make definitive decisions on whether data is kind of like even or not, or distributed differently to how we'd expect. So that might be a little bit theoretical, but the main thing to get your head around is we need certain kind of ingredients for a hypothesis test. We need a null hypothesis, and then we need an alternative hypothesis, and then we also need some kind of idea of how our data is going to be distributed, because a lot of these tests will have some kind of like prerequisites for the data, or like conditions on the data for it to work. So before I bore everyone with mathematics, let's get into a very quick example. We have here the scores of IQ tests for men and women, and the way this data was collected means that the scores for men were in the first 21 entries. So what we can do here is we can say 0 to 22, but because this is a 0, we can take a shortcut and just do this. And that means that because it's kind of like a binary choice, the data for women is from the 22 onwards, so we can do this. So that's a nice example of why this little odd kind of formatting where it stops at 22 is quite nice, because we can use 22 in both of these boxes and it makes sense. So we can say, I'm just going to not print men and print women because that's a little bit boring. But what we end up getting here is, I think there's 50 data points here, and we have a kind of like an uneven sample size. So there are far more women in our sample than there are men, but that's okay. So what we want to be testing is, are the two sample means equal? Sorry, are the two population means equal? We're going to be looking at the sample means. So the null hypothesis here is that men have the same IQ score as women on average. So the mean men IQ score is the same as the women mean IQ score. Sorry, there's a mouthful. And because we can't, in real life, we can't take the entire population and say we know the exact mean. We're going to have to take a sample mean, and the sample mean is going to have some kind of randomness within it. So behind the scenes, what is happening here is we're going to be looking at this randomness, and we're going to be manipulating this randomness in a way that mathematicians do until we can kind of put some kind of knowability on it, and a lot of this is to do with the normal distribution. What we're doing behind the scenes is we're manipulating the randomness so that it kind of fits into this standard normal distribution or something like it, so that we can kind of definitively test what's going on. So the modules we are going to be looking at, scores is not defined, but scores is defined. It's because I haven't put scores. There we go. The modules we're going to be looking at is the stats in the SciPy library. And there's two ways of importing this. We can do from SciPy import stats, which works, or we can do import scipy.stats as stats, and they're both pretty much identical. We're going to get very identical kind of results whatever we do, because we're just going to be kind of getting the functions from the stats library, so it doesn't really matter what you do. And then the test we're going to be looking at is the independent two-sample t-test, and the test that you will need will depend on the data that you have, the kind of analysis that you want to make, the conditions of which your data has. So if your data is not kind of normally distributed, as we've assumed here, certain tests won't work, but they might be robust, which means they kind of will work but won't be perfect. It's quite complicated, but you will need to look at what kind of data you have to decide what test you need, is the point I'm trying to make very badly. But that's what you need to be looking at. So we're going to be looking at the two-sample independent t-test. So what this means is we have two samples. We have the men and women samples. We're going to be testing that they're equal and they're independent, which means that there's no relation or pairing between the two. So one man and so one kind of result from our man sample doesn't correspond to one with our women. So an example where this would be the case is if we had like a before and after experiment. So kind of like a car was put into a garage and we had to say what its petrol consumption was before and after that, and we did that for 20 cars. That would be a pairwise test, but we're going to be looking at an independent test. So the test we're going to be looking at, I'm going to put this all in one print because it's very simple, is stats.t-test underscore ind, which is independent, and then we're just going to pass the two lists, and you can do this with NumPy Eraser as well, as arguments. We do shift enter, and then we get the results. We see the statistic here, which is the statistic we're going to be looking at, which then we can use with a t-value table if you're into that for some reason, but the only value that we're going to be looking at is the p-value. So the p-value is the probability that we get, or the probability that we have the data that we have based on the null hypothesis being true. So the probability of us getting all this data, given that the men and women have the same IQ, is 0.788, so around 80%, and that's well within the margin of error for us. We can easily say here, we're very comfortable to say that men and women have the same IQ. Well, I mean, which we should, but we're extremely comfortable to do that because there is a huge probability that this is the case. 80% is massive in statistics. In general, anything above 10% is like we can't reject the null hypothesis with any kind of and feel good about ourselves. Anything below 10%, we can start to look at it, but anything above 10%, we're like, whoa, we can't do anything here. Yeah, 5% is generally the margin of error that we're going to be looking at. So that's been an introduction into hypothesis testing. I hope you've enjoyed it. Next time we're going to be looking at ANOVA, which is another form of hypothesis testing, but it's a little bit different. So hopefully I'll see you then.